Right, welcome back. So this is my second video looking at my 6-inch race quad using features from ArduCopter 4.5. So there's some good new features in 4.5. My first video was a simple one, looking at the PID notches, very easy to set up and great for attacking frame resonance. So this video is going to be a little bit more complicated because we're going to look at D feed forward. To illustrate this, probably easier to see a copter. So here's my copter. You can see my copter here. Now, if we look at it endways like that, so when you provide some input, let's say you're going to roll like that. The way the control system works is that the input is requested, and then there is a determination of the difference between the target, what's requested, and the actual roll, so that error component. Let's say I push the stick all the way over, and if the copter's nothing's happening and the stick's all the way over, and so the error is quite large, and then it will accelerate to accommodate that stick input until I reach the requested roll rate or roll angle. Now, that detection of the error takes some time because you have to first create the target, then you've got the error determined, the PIDs are changed to adjust for that error. And it means that these very sharp movements, particularly if you're trying to do a flip, can end up not being as sharp as you'd like them. But there is a way around this, which is that if you know the sort of capabilities of the copter, if you know what acceleration in roll it's capable of, you can feed that request directly, feed forward it's called, directly into the controllers. Now, there's a little bit of a danger here because if you feed too much, you get oscillation. But if you calculate it correctly, then you can basically apply direct input into the motors based on a target request, and so you can get much snappier movements, particularly in flips and so on. Now, I showed this in previous videos with regular feed forward. So regular feed forward is the input required to achieve a fixed rate, whether roll, pitch, or yaw. So, you know, what is the rate? What is, if you're basically going to continue flipping the copter over and over and over, what is the maximum that it can do that at, and what rate input needs to be provided to sustain that rate? So that helps with sort of continuous motion like that, but it doesn't help with acceleration. And so with acceleration, what you want is the derivative of the feed forward to be inputted so that you can calculate the input necessary to achieve a target acceleration. And that derivative of the feed forward is what's being implemented in the PIDs, or what I implemented in the PIDs in 4.5. So that's all well and good. D feed forward is just a number, it's just a play. It's very easy to apply. The code for actually applying this is relatively straightforward. The complicated thing is, how do you actually calculate the value that you need? So let me switch to a log and we can start having a look at this. Okay, so rather frustratingly, I turned off the mic. So I'm going to dub this over using my Yeti mic. So the audio quality should be a bit better, but I'll try and mirror what the other me is saying. So the way you test this, and this is what I'm saying, the way you test this is you basically put a copter into hard roll and pitch back and forth, roll right, roll left, roll right, roll left. And in that middle phase, you should get a constant acceleration, and it's the constant acceleration that you're looking for in the logs to try and determine what D feed forward is. And so what I'm doing is I'm bringing up the roll. So you can see the roll here, the actual achieved roll. And then I'm going to compare that with the actual stick input. You can see pitch. Also, I did sort of a bunch of rolls and then a bunch of pitches at the end. So we're just looking at roll here. So if we look at the roll input, the RC1 input, and zoom in a little bit on this kind of second bump. And what you can see is that we get the hard roll right, and then the actual roll catches up some period afterwards. And so there's this latency that I was talking about earlier. And what we're trying to do is eliminate this latency by using D feed forward to provide direct input into the control. And that should eliminate the latency and lead to much crisper response. So if we get rid of the RCN and probably get rid of the roll as well, and we're going to switch to the rate output. So the rates, this is the actual roll rate rather than the roll absolute value. So this is in degrees here. And now we're going to look at the roll rate in degrees per second. So again, looking at that little bump there, you can see that the roll rate bumps up first. Yes, you can see the rate ramps up before the actual roll kicks in. And what we're looking at is the acceleration of the rate, so the angular acceleration here. And we're looking for a sort of constant acceleration, and that's what we're going to measure and calculate the value of, and find out what we want to find out. What's the constant rate output that results in that constant acceleration. And so yeah, you can just see the difference between the roll and the roll rate. And also we're looking at roll desired versus roll actual. It's the roll actual that we're really interested in for that constant acceleration. Obviously, if they diverge a lot, then we have to be a little bit careful there. So if we gonna get rid of roll here and just look at the rates now. So this is R and R des. And then we're going to look at the roll out, and again look at this bump here. So you can see the bump here, this one. And what we're looking for is a sort of constant roll out value for that constant acceleration. Now it's a little bit difficult to see, and a little bit difficult to determine. You can see these sort of got these big spikes in roll out, and we want a constant value, so it's a little bit difficult to determine. And so for this one I picked originally, there's not a sort of constant value, and so not really sure what we're going to choose there if we try and do a calculation on that. So instead I'm going to pick this other one, which has a more constant rate out value. So you can see that the rate out is sort of constant for the flat line bit of this green line, which is the R desired. And so what we're going to do is a calculation based on that R desired value where the acceleration is constant, roughly constant. So we're going to zoom in a little bit. So we'll just zoom in. There we go, on that straight line bit. So we're just looking for the flat line. There we go. And where a value of rate out is sort of constant, and even there it's not that constant, and so I think probably we're going to have to find
another one. You can see it's a little bit of an art rather than a science trying to get these right values, and a lot of that's down to the way the copter is handled. Now, probably what we should really do is write some kind of scripted auto mission that does these constant outputs, and then we could get a much more precise value rather than me with my twitchy fingers. So we'll just find the next bit. Okay, so we got there's going to pick another spike. Okay, and we're going to pick this one here. So it's negative, but you can see the rate, the roll rate out is somewhat constant. Somewhat, I say. He says roughly. This is where the numbers are important. You can't see it on the screen, but I'm going to use show point values. And you can see that roughly the rate output is roughly negative 0.32 for a constant period. And then the roll desired goes, so it's got time units here, and we can see just about at the bottom there's the time in milliseconds, and so we're going from 682 milliseconds to 713 milliseconds for this flat part of the graph where the rate out is constant. And so we can get sort of precise values by again using show points under cursor. And so we're going to go from the sort of white dotted line on the left to where my cursor is now, and that's 682 milliseconds to 713 milliseconds. And we've already measured the rate out, which is minus 0.32. And then what we also need to know is what the actual rate is in degrees per second. And that goes from minus 122 degrees per second to minus 322 degrees per second. So it's an acceleration from 122 to minus 122 to minus 322 at roughly constant rate, constant acceleration, sorry. And now what we're going to do is a calculation based on those numbers to come up with the D feed forward value that is required to achieve that constant acceleration by direct input. So I'm just reading off the numbers here. Past me is a little bit slow to catch up, clearly. Future me is a bit quicker, because I know what's going on, because I've seen it all before. And so yeah, this setting in mission planner where you show the point values just shows you, will show you individual points from the log, so you can get very precise measurements. You obviously want things to be at the same time when you measure them, so you don't want to have a different set of points for the rate out versus the roll rate. So yeah, roughly I'm reading off minus 0.32 there. So what we're going to do, so we've written all those net numbers down. What I'm going to do now is switch to a little bit of text-based maths using TextEdit in my trusty calculator, and I'm going to show you how I do that calculation. So here we go. Here's the text editor, and just a sort of recap of the values that we had before. So first up, the time period that we're talking about. So we've gone from 682 to 713 milliseconds. So the time period is one minus the other, which gives you 201 or something. No, 31, sorry, milliseconds. 31 milliseconds, so that's the time period. And then we're next going to calculate the change in rate output in degrees per second. So again, minus 1 from the other. So we've got 322 minus 122. So that gives us a change in rate of 200 degrees per second. So 200 degrees per second in 31 milliseconds. So now we need to calculate what the angular acceleration is of that. So basically the acceleration is the difference divided by the time. So we're going to divide 200 degrees per second by 31 milliseconds. So we'll just see that. And 31 milliseconds in seconds is 31 divided by 1,000 milliseconds in a second, which gives us 200,000 divided by 31, which equals 6,400 or something like that degrees per second. 6,451 degrees per second. Now, we actually want the answer in radians, so all of this stuff works in radians, and so we need to convert that degrees per second value into radians per second. And so we do that by dividing by 180 and multiplying by pi. So multiply by pi, divide by 180, and that gives us 112 radians per second. Okay, and then my OCD is making me tidy this up a little bit, but not strictly necessary for the calculation. And so what we want is d feed forward, therefore, is the rate out per radian. So we basically read off the rate out, which is 0.32, and divide by the radians per second. So we get 0.32 divided by 112.6. So just going to show you that here. 0.32 divided by 112.6, which gives a very small number. Naught 0.00284, I believe. My memory serves me well. Yeah, 0.2000284. And this is very common of d feed forward, that you get these very small values, and it's important that you don't make this value too large, because that will lead to oscillation, because you're sort of providing too much direct input. You can also see that it's a bit of a convoluted and somewhat approximate calculation. So if we look at the parameters and see what I got for this copter, you can see that for roll, for pitch I got 0.000431, and for roll I got 0.000443. So same order of magnitude, but somewhat different values. So clearly I chose another part of the graph. The main thing is smaller is safer. So don't err on this high side, but obviously the more accurate this is, the crisper the response will be. So these are the values that I calculated earlier in the field, and they seem to work pretty well and give me pretty good output. And yaw I tend not to do, because yaw doesn't really need this level of precision. It's only really roll and pitch where you want to have a very crisp response, where yaw is not such a big deal. And that is it, to all intents and purposes. So a bit of a complicated one, this. Not helped by my inability to make sure that the sound is recording, so apologies for that. Hopefully the better sound quality from my Blue Yeti mic will help there. But yeah, let me know how you get on in the comments. Obviously, if you need help sorting this out, please ask. I'll help you. But what you do get is this much crisper response on roll and pitch, particularly in flips and rolls. You can start very suddenly, stop very suddenly. It just feels a lot crisper. So yeah, thanks for watching, and tune in for my next video whenever I get that done. Thank you very much.